Let's start with the classical electrodynamics, and after a very long time, almost 3 months, we are back to the classical electrodynamics lecture series. And as you know that we have already completed a couple of lectures in chapter 3, which are the boundary value problems to electrostatics, and we have solved the Laplace equation and spherical polar coordinates. But in addition to those couple of lectures, we have exactly followed Jackson, and now in this solution I will slightly differ with Jackson, and especially in the recursion relation and the derivation of the Legendre polynomials. We will deviate a little bit from Jackson for a conclusive and comprehensive understanding of the Legendre polynomials. So let's start here. We did some A's or potential, which is phi is a function of r, theta and phi. And in spherical polar coordinates, we have discussed in the earlier lectures this thing, that what are the spherical polar coordinates and what are their limits and how they make a sphere. So starting from the Laplace equation, del square phi equal to 0. Now del square I can write in spherical polar coordinates. We will have to differentiate between this phi and this phi. So this phi is our potential and this phi is a variable. So doing the separation of variable techniques, let me write that phi, which is a function of r, theta and phi, I write is u of r, u being the potential, which is a function of r, which is only dependent on r variable, and then I write p, capital P, which is a function of theta, and q, which is a function of phi. So u, p, q are actually potentials which depend on separately on r, theta and phi. But as we are having here r times phi, so here I utilize a tactic that I consider this is u by r. Now this r will multiply here and our calculation will become a bit easier. So I will now write this thing, and when I write it like r times phi, now I am not writing the variables, but r times phi is equal to u, p, q. Now for r phi I will have to write u, p, q, and when I write this thing, we have simplified this in earlier lectures, and when I multiply, when I substitute for phi, this thing are r pi u p q, and I multiply with the r cube sine square theta. So multiplying with r cube, substituting this one and multiplying by r cube sine square theta divided by u p q. Then we will get our equation is r square sine square theta 1 over u d square u over d r square plus sine theta by p d over d theta and sine theta dp by d theta plus 1 over q d square q by d phi squared, and this thing is equal to 0. Now I am not doing the individual steps here because we have already done them in the previous lecture. So we are having finally this equation, and now from this equation, let I call this equation is equation 1. So I can write that means I will have to split this equation now. If I look here, then this part, the first part is a function of r and theta. If I look here, then this is a function of theta only, and this is a function of phi only. Now if I consider only this portion, and if this portion is equal to a constant, let's say that constant is equal to m square, then this portion will be equal to minus m square, and the result will be equal to 0. So I write 1 over q d square phi. So I will write this d square q by d phi square equal minus m square. Now this one I can further simplify, that 1 over q d square q and d phi square is equal to m square, and now I can solve this differential equation, and the solution of this differential equation is q m. I will put an index here, and this is a function of phi equals some constant which I will ignore at the moment here, and plus minus I m and phi, which is equal to cos m phi plus minus I and sin m phi. So this is the solution of this part. So we have compared it to m square, this portion, and this portion to minus m square, and we got this solution. And here we say that in geometries where full range of pi is available, then in order to have the constant m and to force that this q, which is a potential, should have a single value, then this m must be an integer. So m must be an integer to force q, which is potential, to be single valued. Now let me explain this a bit, that what is meant by this thing. M is a constant. Now this constant should be an integer, not non-integer. So why this is to be integer in order for q to be a single valued function? Let me elaborate this a little bit. Let's say we consider a sphere, and this is the coordinate system, and I consider this is a sphere which is in the spherical polar coordinates, and on this sphere, for any point that I consider, this point should be having a single value of potential, which is q here. Now what does this mean? This means that we are having two functions, cos and sine, and these functions I call periodic functions. These functions are actually periodic functions. So periodic functions means that when we have this value, for example, I know that phi is sweeping along the plane of x and y, then any point on this sphere along phi, I will have, for example, I'm having the value of phi. So for the phi, q should have one value. Then, being a periodic function, if I move this point up to 2 pi, like I'm on the surface of the sphere, and any point on the sphere if I consider, then if I move 2 pi, I will again come to that point. Similarly, if I move in reverse, I will come to that point. So it means plus minus 2 pi will again give me the same point. Similarly, phi plus minus, instead of 2 pi, if I move another 2 pi, so this will become 4 pi, means earlier here we were having multiplied with 1, now we are having multiplied with 2. So 4 pi means I know another 2 pi, that point will come again. Similarly, phi plus minus 6 pi. Now this will again continue, in any 2 pi rotation I will be there. So I can say that this is equal to phi plus minus and m times 2 pi. So I can write 2m phi. Now m should be an integer. M should be an integer, and this m, integer means it can have plus value, minus value, and this will be 0, 1, 2, 3, and so on. So 0 plus minus 1 plus minus 2 plus minus 3. This is plus minus 1, this is plus minus 2, plus minus 3, and so on. So m is having actually these values. If I consider m to be non-integer, for example, m is equal, instead of 1, it is equal to, let's say, 0.5. Now what will happen? Let's say I'm reaching this point. So this point on the sphere is, let's say, at certain pi. Now when I will not reach 2 pi to that point, but I will reach half here of pi. So I will be somewhere here on the surface of the sphere, and this will make the 2 points not unique but different points. And that's the reason that mathematically this m is supposed to be an integer, while non-integer values are not acceptable because they will give us 2 different points. And that's the reason that Jackson is writing that m must be an integer to force q to be single valued. If for non-integer, we will have 2 different values of q. And with this, I will say that we will have to proceed further with our equation. Now our equation, this one is done and we are left with this. So this side is equal to m square. So I can write that r square sine square theta by this r square sine square theta 1 over u and d square u over d r square plus sine of theta and divide by P d by d theta and sine theta d by d theta. This sine theta is actually with this. So sine theta dp over d theta. The second term, sine theta by this, is equal to m square now, because the earlier was minus m square. So let me divide this whole by sine square theta. So if I divide by sine square theta, then what I will get? I will get that r square 1 over u, r square over u, and d square u over d r square, plus sine theta 1 will cancel with this and 1 will remain here, plus 1 over p and sine of theta d by d theta and sine theta dp over d theta. Then this will be equal to m square over sine square theta, so I can move it inside the equation. M square over sine square theta is equal to 0. So this is our equation, and now let's consider for another constant. If I look here, then this portion is one term, then this portion is another term, and here we are having another term. So this one is now a function of r, this is a function of theta, and here it seems like only a function of theta, but we are having m square here, and m was actually a function here, means on the other side we were having phi as well. So this one is actually theta and phi. So let me write this thing, that we focus on this equation, and this equation, which is the radial part, let's consider that this portion is equal to a constant, and that constant is alpha square. Then this will be equal, this whole will be equal to minus alpha square. Then we will have our equation equal to 0. So let's start with this, that r square over u, d square u over d r square is equal to alpha square. So further I can then write that d square u over d r square is equal to alpha squared over r squared and u of r. Now if we write that, let's say u is approximately equal to r to the power rho. Now why I'm writing approximation? Because I'm not considering any constant here. So this is approximately equal to this. I can write that, what about u prime? Means du by dr. So this will be equal to rho r rho minus 1. Similarly, u double prime will be equal d square u or dr square, rho into rho minus 1 and r rho minus 2, minus 1 minus 1 minus 2. So we are having our equation like this, and now just putting back the values here, so I will have rho into rho minus 1 into r rho minus 2. This is equal to alpha square over r square, and for u I will write r to the power rho. Now this is equal to alpha square r to the power rho and r2, so we will have r rho minus 2. Now r rho minus 2 here is cancelling with r rho minus 2, and we are left with rho into rho minus 1 is equal to alpha squared. Now this has to be kept in mind that both rho and alpha are constants, the undetermined constants. We haven't found their values, and this is one of the algebraic tactic to write alpha equals alpha square equal to L into L plus 1, where L is a constant, so it will become L square plus L. This will ease our calculation, so we can write that rho into rho minus 1 is equal to L into L plus 1. So I can further simplify this.